In this lecture, we will start a new kind of method, which is conjugate direction methods. So first we will discuss the concept of conjugacy, then some properties, and then we will cover one method. In the next lecture, we will cover some more methods in this class. Okay? So in n-dimensional space, when you have two vectors, d1 and d2, vectors or directions, which satisfy this kind of relationship with respect to a symmetric matrix A, then you say that these directions d1 and d2 are conjugate to each other with respect to this matrix. Okay? Now, conjugacy of directions is of little utility unless the matrix sitting inside is positive definite also. Okay, so now onwards we will discuss conjugacy of directions always with respect to a symmetric positive definite matrix. Now, what positive definiteness does to the conjugate directions? Positive definiteness of the matrix A implies linear independence of the conjugate directions. That if they are conjugate, then they have to be linearly independent. And you show that very easily, that you take a linear combination of the conjugate directions as 0, and then from that you try to see if that necessarily implies each of the coefficients being individually 0, because that is the formal check for linear independence of vectors. So you take this sum as 0 and then say that we will pre-multiply it, the entire equation, with di transpose A, where di is one of these. Okay, so since they are conjugate, so di transpose A d0, di transpose A d1, all but one will become 0. The one which has di here already sitting earlier, that will become ci times di transpose A di. Now since the two are same, this is not 0. Rather, we know that this is positive because the matrix A is positive definite. So this is the role of the positive definiteness of the matrix. So in that case, di transpose A di becomes positive, so Ci has to be 0. And that applies for each I. And therefore, this linear combination equal to 0 will mean that each component is individually 0. And that means that these are linearly independent. And that also means that in n-dimensional space, at most n conjugate directions are possible. After you have got n, which are mutually conjugate, then you know that you have exhausted the space. And this is of value. And the value is this. If we try to minimize this convex quadratic function in Rn by line searches along several directions, which are conjugate, mutually conjugate, that means each of them is conjugate to every other. Then, with these line searches, with updates like this, after you have got several steps and you have reached the point k plus 1, xk plus 1, okay, I mean, by the time you reach xk, after that you execute this particular iteration, k plus 1th iteration, and there the line search result alpha k is this. This is one point. And the second is that this xk actually has minimized the function not only along the direction of the current line search, but over the entire subspace that has been traversed through all these directions, through all these line searches along these directions. This is the expanding subspace property. Okay. So this is important. So the first one is easy, which we have already seen earlier in the context of other gradient-based methods. Now, this one, that is this, for this we can see one clearly how it works. Say after the line search starting from xk along direction dk, the result alpha k that we see. So at the end of that step, wherever we reach, that is xk plus 1, if you evaluate the gradient at that point, that must be orthogonal to the current direction. Otherwise, the line search would not stop there, right? So in this direction, the rate of change is 0 at that point. For that, this has to be orthogonal. And therefore, you now express the gradient as ax plus b at that point. And xk plus 1, you know, is xk plus alpha k dk. Put that here. And then axk plus b is the gradient at the present point. And then remaining alpha k dk is sitting here, multiplied with a. Okay. Now open this and you get dk transpose grad q at xk plus alpha k times dk transpose a dk, that is here. And from here directly you get this formula, because this has to be 0. So this sum has to be 0. So alpha k is minus this by this, that is this formula. Okay. So the first part is easy, and this also sets the stage for the second one, because this, when you put k equal to 1 here, the second one is also implied for k equal to 1 for that specific case, and that serves as the trivial case for the induction argument, because for k equal to 1 only one direction has been covered, that is d0, and this is the case where through d0 it has been minimized at x1. Okay, so put k equal to 0 here to get the result for k equal to 1 here. Okay. Now, since we have already covered the trivial point of the trivial case of the induction argument, then we go for the rest of it. We assume the second result to be true for k equal to j, and that will mean that xj minimizes the function over the j dimensional planar section, the cut section in the n dimensional space, and that means the gradient at xj is orthogonal to this entire subspace, the span of all these directions. That means this gradient is orthogonal to each of these directions. Okay. Then for the next step, you again impose this, and now you have this similar sum. Now the claim is that this new point will minimize the function over the old entire j plus 1 dimensional planar section, over the old directions as well as the current direction. Okay, dj. So for the old directions, that is I not equal to j, I less than j, you say that this is already implied in the induction hypothesis. That is, grad at xj is orthogonal to all the previous directions, 0 to j minus 1. Okay, less than j, all covered. And this is 0 because of the conjugacy of directions, because dj is a conjugate direction to all the earlier ones. The directions are mutually conjugate. So for I less than j, this is 0, this is 0. So the sum is 0. And you have got what you wanted for j plus 1, k equal to j plus 1. For I equal to j, that is for the most recent direction, which has been just covered, okay, through which you reach this point. For that, Neither this is 0 nor that is 0. But the definition of alpha j is minus this divided by this. So the sum is 0. Okay. So as a result, you can say that for all I from 0 to up to j, this is 0. And that means that the statement, the claim holds true for k equal to j plus 1 also. And the way induction argument goes, based on that, you can say that it is true for all k up to n. Because after n, this gradient will become 0 and the method will stop and we have no issue to proceed. Okay? So this is the advantage of conjugacy of directions. That is, if the directions of search are mutually conjugate, then through line search, a current step minimizes along this current direction, but whatever the minimization that took place in earlier steps, it does not spoil that. Okay. And steepest descent iterations were spoiling a part of the previous iteration's task. And that conjugate direction method will never do. Okay, so that is the idea. And that means that a quadratic function will get exactly minimized through at most n line searches along the conjugate directions. Now, we started with the understanding that we have n conjugate directions in our hands. Now the question is how to get them. Okay. How to work out a sequence of n conjugate directions. Any answer to this question will give you a conjugate direction method. If tomorrow you come up with a new way to get n conjugate directions, then there will be a new conjugate direction method. Now, what are the existing ways? One is something which is very trivial, and that is actually a generalization of the Gram-Schmidt process. The main basic Gram-Schmidt process is a process for orthogonalization. Okay, that is for developing an orthonormal basis for the subspace spanned by a few vectors in n-dimensional space. Here, we talk about a generalization of that for getting not orthogonal directions, but conjugate directions. Understand that the conjugacy is actually a generalization of orthogonality, because in orthogonality, you talk about two vectors being orthogonal when they satisfy D1 transpose D2, which is D1 transpose identity into D2 equal to 0. Here, that identity matrix sitting in between, in the case of orthogonality, is replaced by some other positive definite symmetric matrix. Identity matrix is also a symmetric positive definite matrix. Now here you have not identity, but a non-trivial positive definite matrix. So to the extent that it is a generalization of orthogonality, conjugate directions can be found by a generalization of the Gram-Schmidt process. Okay. So you start with a set of linearly independent vectors, starting with the natural basis vectors. The coordinate directions will be good enough. As the first direction in the family of conjugate directions that we are going to build, you keep the first one from here. That in this case would be E1. Okay. Next point onwards, at any step, you propose dj as the jth one from this top, vj, plus a linear combination of the earlier directions that you have generated. And then simply demand this to be conjugate to all the old ones sitting here up to j minus 1. And the demand is put very easily. The same thing that we have been doing all along. You pre-multiply this with matrix A and then with di transpose. Then you will get di transpose A dj, which you will set equal to 0. Okay. And here you will get di transpose A vj plus From this sum, all of them will go out because of the conjugacy of the old directions among themselves, except Ci di transpose A di, and that will remain only one. And from that you will get Ci by saying minus this divided by whatever comes from here. So minus di transpose A Vj divided by di transpose A di. Okay, this is certainly positive, so you don't have to bother about dividing by something. So like this you get each Ci, and that you do for j equal to 1, you get d1, which is conjugate to d0. That you do for j equal to 2, you get d2, which is conjugate to both d0 and d1, and this goes on. Okay. This also has utility, not this, conjugate directions also has utility in solving linear systems of equations, large ones. Okay. Now this process is simple to understand, but it is not efficient because it has got too many matrix vector products here, and that so many times for so many Ci's, and that for each j, that means inside cycle another loop, lots and lots of loops, okay, inside. So that will mean quite a bit of computational burden. Okay. Besides, here we are um, doing or thinking as if we collect all the directions first in hand before embarking on minimizing through line search along each of them. But that means the directions are generated without any recourse to the objective function. Okay, so they may not be very good directions for that objective function, and they may appear in haphazard order. But the most troublesome point of this method is that even though the generated directions are nominally and mathematically conjugate and therefore linearly independent, but sometimes it happens that they are just nominally linearly independent. Actually, the new direction makes just a small 5-degree angle with an old one, or a 5-degree angle with the plane of two old ones. Okay, so that way the new direction will not be much of a new direction in which the search will produce something reasonably significant, because it's another search along another direction which is at a very small angle from this has already been done, and that is one big issue. Therefore, this is not how conjugate direction methods typically generate directions. They generate directions based on other considerations, one of which we are just going to discuss. And that is parallel subspace property. Suppose we conduct two line searches starting from x0 and starting from x0 prime along two parallel lines along the same direction, x0 plus something d and x0 prime plus something d. This is one line search which gives us alpha 0. This is another line search which gives us alpha 0 prime. At the end, through this line search we reach x1. Through this line search we reach x1 prime on two parallel lines. One line going from x0 to x1, another line parallelly going from x0 prime to x1 prime. Now, x1 is the minimum of the function along this line. x1 prime is the minimum along this line. So the gradient at both x1 and x1 prime will be orthogonal to this direction d. That is this as well as this. Both are 0. So their difference is also 0. D transpose this minus this. But the difference of the gradients at 2 points for an orthogonal function is simply a times the vectorial difference, x1 prime minus x1. That is this. Then this equation equal to 0 tells us that this step delta x from this arrowhead to that arrowhead of the two line searches, two parallel line searches, that vector is orthogonal to the direction d. Not orthogonal, conjugate. That is conjugate to the direction d. So this can be a way to generate new conjugate directions. Okay, and this is particularly useful because it operates for not only a single direction but over a collection of directions. Say xk and xk prime are minima of this function over two parallel sections, two parallel planar sections. So like this, you have two parallel sections. Okay, both the parallel subspaces are constructed of a bunch of directions, k directions, the same k directions in that. So one planar section can be represented as x0 plus this subspace, other one is x0 prime plus that this same subspace. And that means that the converged points after the line search, xk and xk prime, which are minima over the parallel sections. Okay, so here also the gradient is orthogonal to the entire subspace, here also on the entire subspace. Entire subspace means each of these directions, and that means that both the gradients at this point, at that point, at this minimum, on this subspace, on this plane, on that point, at that point, on that plane, both gradients are perpendicular to each of the directions that constitute that planar section. Okay. So you say di transpose this is 0 and di transpose this is 0 for each I, constructing that bk subspace. And if you subtract them, then you get this for each I. And that means this new arrowhead to arrowhead vector, this new delta x is conjugate to all the directions in this. And if you already have k directions, now this delta x will give you the k plus 1s direction. Okay? So this will be a way, a mechanism to generate new conjugate directions when you already have a stock of a few old ones. And this is what Powell's conjugate direction method does by a clever scheme of starting different line searches from different starting points. So what it does is, and make note that Powell's conjugate direction method is a direct method. It does not use derivatives. Inside we are talking about gradients and so on, but derivatives, this method will not evaluate, will not use. It will do only line searches, only function evaluations. So initialize the direction set. Now we are not calling them from D0, we are calling them from D1. D1 to Dn, maybe by E1, E2, E3, E4 up to En. That is 1, 0, 0, 0, 0, 1, 0, 0, and so on. Okay. N directions, initially set along the coordinate directions. Then first conduct a line search along the last direction, Dn. Okay, last in the list. If necessary, you will put it negative, because when you start searching along that direction, if you find that along positive Dn the function increases, then you will go along negative Dn and call that as Dn. Okay. Now it will not be anymore En in that case. But those E1, E2, E3, E4 will be slowly replaced with conjugate directions which get generated in the process. Conduct this line search and update. Call the point as x1. And now actually iterations start. Put k equal to 1, basically cycles start. Then starting from this point, x1, for the time being. In the next iteration, in the next cycle, it will be from x2, next x3, and so on. In a series, you conduct n line searches along d1, d2, d3, d4 up to dn. So at the end, you reach this point that starting from xk, you have conducted n line searches. Okay, and put the final result at x prime. Now you see, x prime has been reached through several line searches. The last one is along dn, and x1 was another point which was found by a line search along dn. So if you now add the two arrowheads, that is a new direction which is conjugate to dn. Okay. If that direction, if this vector is very small, that means you have converged, you stop. Else it is a new conjugate direction. And now you want to store this direction as a new dn, and the old dn is now to be stored here. So you start from this end. Old d1 gets thrown out as old d2 is overwritten on it. Then d3 is overwritten on d2, and so on. So the new d1, d2, d3, d4 up to dn minus 1 will be actually the old d2, d3, d4 up to dn. So the space for dn is now empty, and a normalized version of this new direction you put as dn now. And then conduct a line search along that and update. Now this becomes your x, k plus 1. Okay. At the end of the first cycle, this will become x2. And then you make it 2 and continue from here again, step 3. Okay. Because this line search along dn, you have just now done here. This is along the new dn. Like this, as you go on, what will happen in the second round, at the end, you would have conducted a series of line searches along up, ending with up to dn minus 1 and up to dn. That is a new dn minus 1 and new dn. And the old sequence actually ended at x2 by another series at the end of which these two directions were there. And therefore, this step in this iteration will now generate a new direction which will be conjugate to both dn minus 1 and dn, and they themselves are also among themselves conjugate. So at the end of the second cycle, you would have collected a set of 3 directions which are mutually conjugate. And like this, you will go on collecting one new every iteration. And that's why after kth cycle, the last k plus 1 directions will be mutually conjugate. And therefore, after n minus 1 cycles, the last n, which are all the directions that are there or that can be, will be mutually conjugate, along which a line search would have concluded finally at this step, at the end of n minus 1th cycle. Okay? And therefore, you have got your solution. That means xn will be the minimum point. So this is what Powell's conjugate direction method does. If you conduct a dry run, imagine that you are running it over a 4-variable quadratic function. I suggest that you take a 4-variable quadratic function, convex quadratic function, and actually run this step by step and see how it works. Okay. So before the cycles start, the first line search will be along D4, which is to begin with E4. Okay. And that ends at X1. In the cycle 1, you would have conducted line searches along the current D1, D2, D3, D4, which happen to be E1, E2, E3, E4, ending at this point. And the new direction that you will get will be this. You will normalize it in due course. And then during the direction reset, this E2 will be in the place of D1, E3 will be in the place of D2, E4 will be in the place of D3, and in the place of D4, currently, this new direction will be sitting. and these last two are conjugate. Then you will conduct another line search along this new D2, this direction basically, and that is the sixth line search. I'm keeping on the count of the line search to make note at the end. Then at the cycle, and in cycle 2, again, there will be total 5 line searches, 4 in the cycle normally, and finally 1 along this new direction. So 5 line searches, 7 to 10 and 11. And in the direction update step, these two will again shift, these three will again shift. E2, which is current D1, will get thrown out. New D1 will be this. So E3, E4, D2, D3. Last three of these are conjugate. In a cycle 3, similarly, another push will be there, another 5 line searches will be there, 12 to 15, and finally 16. And by that time, all 4 will be conjugate because now it will be E4, D2, D3, D4. E4 turns out to be the final D1. Okay. So in 16 line searches, the quadratic function is minimized. That is at most 16 line searches. Convergence could have come earlier also. Okay. So you run it on a numerical problem with positive definite matrix A sitting in the quadratic function and actually see how the conjugate directions are generated and updated. Now, we have already discussed. Now let us summarize once. For a convex quadratic function, after n-1 cycles, the direction set will contain the n recent directions of line searches. These directions will be mutually conjugate, and the matrix A underlying this conjugacy is actually the constant Hessian matrix of the quadratic function. And the algorithm will have converged to the minimum point. The minimum point I'm telling because there is a unique minimum point for positive definite A. Now, total number of line searches is initially 1 plus n minus cycles, each cycle n plus 1 line searches. So total n square line searches. So that is why in the 4 variable case, we found 16 line searches according to the algorithm. But then till now, it is only for a quadratic function for which we actually knew the solution analytically all along. The solution happens to be minus A inverse B as long as A is positive definite. We knew that. So it is not the quadratic function to minimize which we are developing an algorithm. Okay. We are developing the algorithm on the quadratic functions and for use in the case of general ones. So what happens? This same procedure run in the same manner. What happens in the case of a general function? On these 4 counts, if you make a little observation, you will notice that the direction set will still contain the n recent directions of line searches, which is procedural, so it will be same. These directions will not be exactly conjugate actually, because conjugacy is with respect to a matrix. Okay. Here, the function not being quadratic, that Hessian matrix will not be constant. And therefore, you cannot really say that all the directions are conjugate. But in small local bunches, the directions may be among themselves conjugate loosely. So you can say, you can expect that directions, say in a 20 variable problem, directions 3, 4, 5, 6 will be roughly conjugate with respect to each other. I mean, conjugate to each other with respect to an underlying matrix which happens to be the approximate Hessian in that neighborhood. Okay. In another neighborhood, say directions 12, 13, 14, the Hessian would have changed. So the directions there would be loosely conjugate around that approximate Hessian. Okay, and so on. Now, when enough steps have been taken and the iterations reach close to the minimum and each step becomes small, then that approximate Hessian with respect to which the local conjugacy holds will become more or less constant. It will be a more or less good description of the Hessian because the steps are small, along which not much changes. Okay, and therefore the algorithm will start converging with a good speed. Okay. However, you cannot expect that in n-1 cycles the algorithm would have converged. So by that time, just one first draft of loose conjugate directions have been built. Okay. So in the case of quadratic function, the first complete buildup of conjugate directions was final. In this case, it is a loose set which has to be operated over for several more rounds. Some small updates will take place, and then hopefully it will converge. So the algorithm will not continue, will not converge, but continue for further cycles. That is why the way the algorithm has been written, it doesn't say that stop after n-1 cycles. It says that stop if a full cycle of line searches produced not much movement. That means you have converged, but not if n-1 cycles have been over. No. So that is why this is the algorithm. And the algorithm operates for general functions also, not necessarily only quadratic functions. And this is a very good method in a way because it uses only function values, no derivatives. And if the function happens to be differentiable, then it gets all the advantages of the gradient being orthogonal to the subspace span and so on. Okay? Otherwise, those advantages are loose and approximate, as best as would be in any method for functions which are not differentiable. Okay. So the convergence properties is every step involves a line search along a descent direction. So global convergence is guaranteed. Now, n-1 cycles of line searches will be roughly equivalent to a single Newton step. So you can perhaps develop a kind of a quadratic convergence result, but in place of the computational cost of 1 Newton step, now you will have n square line searches sitting, okay, which is perhaps not really nice, okay, but you cannot expect this derivative free method to match the Newton step in the best of its locations. The good news is that what Newton steps does not guarantee, this guarantees, that is global convergence. Now, in local convergence, it is certainly of quadratic convergence type, but with a poor proportionality constant than Newton step. But compared to steepest descent method, this is reasonably better because steepest descent method developed its direction based on just the local information. Conjugate direction method uses the history of previous developments and progresses based on which it typically develops a good method. Okay, good direction. One thing that has to be kept in mind is that Powell's method uses a lot of line searches, and therefore, when you implement it, you should use a line search scheme which is fairly efficient, and certainly one that uses no derivatives, because the actual method does not need derivatives. It is its selling point. Its selling point is that it is a direct method. Now, inside that, if the line search uses derivatives, it will be very sad. Okay. Now, one concern which appears quite often is that linear dependence problem. Now, again, remember what we discussed earlier, that nominally the new directions are conjugate, therefore linearly independent, but the angle made by the new direction to one of the old directions or a combination of a few of the old directions may be very small, in which case the new direction may not be practically linearly independent compared to the old ones. Incidentally, this problem, this is disturbing issue, is often remedied to a great extent by a clever and funny remedy. And what it does is that our plan in Powell's method of replacing the oldest direction, that is pushing out the oldest direction during the direction reset, direction update business, we revise that and say that we don't push out the oldest one necessarily. Rather, among the old n directions, we push out that from the direction set, along which in the previous cycle, the benefit was highest. Okay? So the direction, push out that direction of the cycle which happened to be the most effective. And this is very interesting. We have got n staff in our office, a new one comes, and we have to lay off one of the old staff members, and we lay off that one old guy who happened to be the best among the lot. Okay? The reason is that the best among the lot is the one along which the line search produced the largest step. And therefore, the new direction, which is x prime minus xk, that has the biggest contribution from that direction. And that is why the new direction has the possibility, the new good direction has the possibility of being linearly independent to that direction, which has contributed most in the development of this. Okay, so this remedy somehow handles the problem. Now, in summary, we can make note of these points. Conjugate direction methods, unlike Stevens descent or Newton method, uses the history of development, history of movements, rather than only the local information. And Powell's conjugate direction method in particular is a direct method, derivative-free method, which uses the parallel subspace property. There are other conjugate direction methods which we will study in the next lecture, which uses gradient. Powell's method does not. Okay. However, Powell's method has one important cost, which this other conjugate direction method will not have, and that is it has to maintain a set of n directions. N directions, each direction with n entries will be equivalent to an n by n matrix storage. Okay, n square storage in large problems. For example, 200 variable problem, 100 variable problem will be an important memory cost. The next conjugate direction method, which we discuss, uses gradient and operates with only vectors, no matrix or matrix size storage. So that we do in the next lecture. At present, we stop at this point.